In the previous lecture, the Gouy-Chapman model for the electric double layer was introduced. This involves several assumptions to simplify what is a complex system of charges. In fact, the Gouy-Chapman model is the simplest quantitative treatment of the diffuse layer that forms at charged surfaces. Our assumptions include a consideration of a uniformly charged flat surface of infinite dimensions, treating charges in the diffuse layer as point charges with concentrations determined by the Boltzmann principle, and limiting the role of the solvent, in this case water, to the influence of its dielectric constant. We also restricted the system to a single symmetric electrolyte and a low surface potential to limit calculations. We begin this chapter by removing one of these assumptions, specifically the treatment of ions as point charges. By considering the size of an ion and its hydration shell, we limit how close such species can approach the surface, which introduces a new region to the electric double layer, a region located directly adjacent to the surface where there exists a separation of charge. This is known as the Stern layer. Rather than complicating matters, consideration of the Stern layer helps justify the general applicability of our previous results and ties the model to experimental measurements of zeta potential. In this lecture, we will also discuss DLVO theory, which brings together our description of van der Waals attractive and electrostatic repulsive energies to produce a total interaction energy between colloidal particles. Non-DLVO interactions, which often contribute to the total interaction energy between surfaces, is also reviewed briefly. On the left is a cartoon representation of the electric double layer formed for a negatively charged flat surface placed in an aqueous medium, as described in the previous lecture. If we no longer consider the counterions to be point charges, but instead treat them as true hydrated ions, we can envision the formation of a layer composed of such ions, which are more tightly bound to the charged surface than others found in the diffuse layer. This layer of bound ions is known as the Stern layer. It is important to emphasize that these species are not specifically adsorbed to the surface, which would result in their partial or complete dehydration. In its simplest representation, the Stern layer produces a significant reduction in the magnitude of the electric potential. This is demonstrated here on the right with a schematic plot of the electric potential as a function of perpendicular distance from the surface along the x-axis. Again, because the surface carries a negative charge, the surface potential is negative. The combination of the charged surface and Stern layer behaves like a set of capacitor plates, over which the electric potential drops in a linear fashion. The effective separation distance between the plates is about the radius of a hydrated counterion, approximately 0.3 angstroms. This small distance, delta, which marks the end of the drop in potential, forms what is identified as the Stern plane. The electric potential at this plane is known as the Stern plane potential. The Stern layer is composed of bound hydrated ions and some surface water, which are likely retained by the surface as it moves relative to the bulk phase. The plane where this separation occurs is known as the slip plane, and the electric potential here is called the zeta potential. It can be assumed with little error that the zeta potential is approximately equal to the potential at the Stern plane. Furthermore, beyond the slip plane is the diffuse layer, for which the Gouy-Chapman treatment described in the previous lecture applies, in which the surface potential is replaced with the zeta potential. This result is important because the zeta potential for a colloid can be measured. The surface potential cannot, and we are most interested in EDL overlap, which primarily involves the diffuse layer. Also note that the zeta potential can be related to surface charge of the diffuse part of the double layer. This can be thought of as the charge density that must be neutralized by the diffuse layer. In addition to connecting electrostatic repulsion to an experimentally measurable quantity, it could be argued that the use of zeta potential also provides a more practical gauge on the influence additives have on colloidal stability. In addition to hydrated ions, which form the Stern layer, a surface placed in water will attract other solutes. And in the case of surfaces possessing relatively low charge densities and surface potentials, other adsorption mechanisms are often at work, in particular those resulting from solutes being pushed out of the aqueous phase. This can include anionic surfactants and polymers and even multivalent coions. Their adsorption builds charge in the Stern layer, increasing the magnitude of the Stern plane potential, which is assumed to be about equal to the zeta potential. As discussed, the charge density measured from this perspective includes such components and thus provides a clearer picture on the influence of stabilizing additives. Another scenario covered by this approach is the overcatenization of a negatively charged surface, which is not an uncommon occurrence with the application of cationic polymers to destabilize an anionic colloid. In this case, the net charge over the Stern layer is reversed, resulting in a reversal for the sign on the zeta potential. Although not shown here, there are scenarios where the assumption that the electric potential at the Stern layer is equal to the zeta potential is tenuous. This includes the use of chemical species that provide steric stabilization to colloidal particles, which we will discuss later. Up to this point, the discussion has been exclusively regarding flat surfaces of infinite dimensions. We discussed both their attractive energies between infinite blocks or slabs and the electric potential that develops at the surfaces of plates, which gives rise to electrostatic repulsion. We also discussed the nature of the electric double layer and justified the use of results from the Gouy-Chapman model using the potential at the Stern plane approximated by the zeta potential in place of the surface potential. This same approach and discussion could have been carried out using other geometries. Results are shown here for two spheres, two plates, assuming results apply approximately for finite dimensions, and for the interaction between a sphere and a plate. The zeta potential for each component is part of the interaction energy equation, and it's important to emphasize that the interactions between components possessing zeta potentials of opposite sign are actually attractive. For now, let's restrict our discussion to van der Waals attraction and electrostatic repulsion between particles, and we will switch from considering interacting infinite plates and consider interacting spheres. Although particles and solids can take on a variety of shapes, including plates, for emulsions and even foams, the particles tend to be spherical or roughly spherical. The idea that van der Waals and electric double layer interactions between particles are additive was proposed independently by two parascientists, the Russians Derygin and Landau, and Dutch scientists Verwey and Overbeek. Their theory is more commonly known by the abbreviation DLVO. As we discussed, convective movement of particles, which leads to their collisions or interactions, is governed by Brownian motion or hydrodynamics, for example, mixing. It is only at close approach, less than maybe about 10 nanometers, that the colloidal interactions predominate. This is where we begin our description of the interaction. The green curve represents the attractive energy due to van der Waals interactions that pull the particles together, while the red curve represents the electrostatic repulsion resulting from the overlap of the electric double layers associated with each particle. The black curve is their sum, the total interaction energy between particles. It can be seen that the total interaction energy passes through a maximum. The height of this maximum is the energy barrier to aggregation. Very analogous to the activation barrier to a chemical reaction, it is the extra energy that must be supplied by the interacting particles for aggregation to occur. If particles have sufficient energy to overcome the barrier, they reach the primary minimum, referred to by many as coagulation. For all practical purposes, this is an irreversible process. On average, particles moving in a colloid possess about 1.5 kBt of energy. Thus, a barrier of just a few kBt should be sufficient to stem primary aggregation. However, it is important to emphasize that this is an average, and there are particles with kinetic energies higher than this, and convective motion further increases this population. A good rule of thumb is that a barrier of maybe 15 to 25 kBt provides for good kinetic stability. It should also be pointed out that such interaction curves often possess a secondary minimum, which is a shallow well where aggregated particles can be trapped. This is sometimes referred to as flocculation. Aggregates here can be easily separated with minimal energy input, a little bit of shaking. To discuss DLVO theory, we begin with an example. We are asked to plot the interaction energy diagram, that's the total interaction energy, as a function of separation distance up to 10 nanometers for the interaction of identical spherical polymer particles in water at 25 degrees C. We are provided with the average particle size or diameter, which is 1 micron, possibly measured via one of the techniques discussed earlier, the Homaker constant, which is given as 2 kBt, which we could look up, the zeta potential of negative 25 millivolts, which can be measured, we will discuss this shortly, and told that the water contains 50 millimolar of a single symmetric 1-to-1 electrolyte. According to DLVO theory, this is simply the sum of the van der Waals attractive energy and the electrostatic repulsion energy for the two identical spheres. With the provided information and the physical constants listed here, the Debye-Huckel parameter can be calculated and the sum of the equations can be rewritten in terms of a single variable, the separation distance. The resulting plot looks as we would expect, with a clear primary and secondary minimum and an energy barrier to aggregation that is quite high, here about 80 kBt, well above the 15 to 25 kBt required for good kinetic stability of the colloid. When plotting such curves, use of kBt energy units avoids having to work with extremely small values. We will use this example as the basis to discuss the impact of various variables found in DLVO theory. Indifferent ions are those that do not have a tendency to adsorb to particle surfaces. That is, they are quite content just sitting in the aqueous phase. These curves demonstrate the impact of increasing the concentration of an indifferent ion according to DLVO theory. The base conditions are those described in the previous example, but the concentration of the symmetric 1-to-1 electrolyte is increased, first from 50 millimolars to 112 millimolars, and then up to 200 millimolars. This increases the Debye-Huckel parameter first by 50% and then up to 100%, decreasing the Debye length from 1.37 nanometers down to 0.685 nanometers, cutting it in half. In other words, adding indifferent ion decreases the thickness of the electric double layer. Compressing the EDL results in a steady drop in the barrier to aggregation, promoting more rapid destabilization. The physical explanation for this is that increasing the concentration of an indifferent ion reduces the distance the electric potential extends into the solution from the surface of a charged particle. This compression of the electric double layer allows for closer approach of particles prior to the onset of repulsive forces, thus increasing the likelihood that their interaction will result in primary aggregation. For the interaction energy, this manifests itself as a decrease in the energy barrier to aggregation. This can be made more quantitative by defining destabilization somewhat arbitrarily as conditions where the energy barrier to aggregation reaches zero. That is, we identify conditions where the maximum in the interaction energy is equal to zero. This provides an expression often called DLVO critical values. For a given temperature, the Hamaker constant is fixed by the material, so the relationship is between zeta potential, electrolyte concentration, and its valence. If we solve for electrolyte concentration at a fixed zeta potential and valence, this concentration is known as the critical coagulation concentration, or the CCC. Using the conditions listed for a single 1-to-1 electrolyte, a critical coagulation concentration of 210 millimolar is calculated, corresponding to a Debye-Huckel parameter of 1.49 inverse nanometers. This result is consistent with the interaction energy plots for these conditions. The discussion assumes that the electric double layer can be compressed at a constant zeta potential. This would require an increase in the surface charge countered by the diffuse layer, something that would be quite challenging in practice. But the assumption was made here to isolate the impact of the indifferent ion. Up to now, we've been considering a single symmetric 1-to-1 electrolyte in the system. We will continue to restrict the discussion to a single symmetric electrolyte, but let's look at the impact of changing the valence or ion charge number Z. Using the same base conditions from the previous examples, these plots show the Debye-Huckel parameter as a function of electrolyte concentration for ions of valence 1, 2, and 3. Previously, it was shown that for this system, the critical coagulation concentration for a 1-to-1 electrolyte is 210 millimolar. A critical concentration was isolated because it's more intuitive or practical to think in terms of concentration. But the DLVO critical values actually identify a Debye-Huckel parameter for which the system is destabilized, which in this case is 1.49 inverse nanometers. For a fixed solvent and temperature, the Debye-Huckel parameter is a function of ionic strength, thus both ion concentration and valence. What the plots show is that for an increasing valence, the concentration of electrolyte required to destabilize a colloid is decreased substantially. From the DLVO critical values based on the assumption of a low and constant zeta potential, it can be shown that the ratio between critical coagulation numbers for two electrolytes is inversely related to the square of their valence ratio raised to the second power. Also, using DLVO theory for high potentials, we can demonstrate the well-known Scholes-Hardy rule, which predicts an exponent of 6. Most experimental conditions and results put this value closer to 3. The previous discussion examined the impact of indifferent ions. These are ions that have no interest in moving to the surface. We next turn things completely around and consider the impact of ions that possess a strong tendency to move to particle surfaces. These are often polyelectrolytes, ionic surfactants, and multivalent ions. The phrase specifically adsorbed ions distinguishes those ions that move into the Stern layer, displacing water molecules that come into direct contact with the surface. As with our discussion on the influence of indifferent ions, we make a bit of an unrealistic assumption here. It is assumed that increasing the concentration of these surface active ions has a negligible influence on the thickness of the electric double layer. In other words, the added ions have such a high surface activity that they strongly impact zeta potential with little or no change in the Debye-Huckel parameter. Shown here are interaction energy curves for a decreasing zeta potential, with all other parameters being held constant. Returning to the DLVO critical values equation, the critical zeta potential can be calculated, which is consistent with our curves. For a large particle radius and/or a thin electric double layer, the relationship between zeta potential and surface charge reduces to that for a flat plate, as shown here. Using this equation and the zeta potentials from the curves, surface charge densities at the slip plane can be estimated. Also, using the critical zeta potential, a critical surface charge can be estimated. This is the charge density value that produces an energy barrier to aggregation of 0. As discussed previously, particles in aqueous process streams commonly carry a negative charge. Commercially, such anionic colloids are often neutralized with cationic polyelectrolytes. For charge neutralization, the charge density of a polyelectrolyte is more important than its molecular weight, and high charge density, low molecular weight polymers are commonly utilized for this application. The isotherms for such polymers are high affinity, and the polymers adsorb to particle surfaces with a flatter conformation, more effectively countering surface charge. Their use efficiently neutralizes charge density and decreases the zeta potential. Such polymers are sometimes referred to as coagulants. An issue with such polymers is the tendency to over-apply them in commercial systems, overshooting the point of zero charge, or the PZC. This can restabilize the colloid with a positive zeta potential. This is often referred to as over-catenizing. Hydrophobic colloids are found throughout industry and nature. Discussing specific types or uses of such colloids would be a nearly endless endeavor. However, it is useful to describe a few of the basic mechanisms used to control such systems. In addition to charge neutralization, which reduces charge density and the zeta potential along with it, other mechanisms are used to destabilize electrostatically stabilized hydrophobic colloids. A few of the general categories are described here, including patching, bridging, and desorption. Patching is an approach used to destabilize anionic colloids of low charge density or possessing particles having well-separated surface charges. For this, cationic polyelectrolytes of higher charge densities and usually of lower molecular weights are used. The polymers are applied at levels sufficient to neutralize charge, but instead of lying flat on particle surfaces, the adsorbed polymers form islands of cationic charge. This produces a patchwork of alternating positive and negative charges, promoting net attraction between particles which strongly bind them together. As a result, patching tends to be viewed as a coagulation process. Note that patching is strongly influenced by ionic strength due to screening effects. In bridging, low charge density, high molecular weight cationic polyelectrolytes are commonly used. These are linear polymers, and it's not so much low charge density as it is optimal charge density. The objective is to adsorb the polymer on particle surfaces with large loops and tails that reach well beyond the electric double layer, allowing for the attachment onto adjacent particle surfaces to form a bridge. Sufficient charge is required to expand the random coil of the polymers, but it must be low enough to inhibit their assuming flat conformations on particle surfaces. The concentration of polymer used is extremely important because the adsorbed polymer must leave sufficient room for the further attachment of polymer chains. In practice, optimal feed levels are well below charge neutralization and surface saturation. Bridging produces strong flocks, but once sheared, such structures are unable to reform. Coagulation, through charge neutralization and/or patching is often used along with bridging flocculation for the separation of colloidal solids. The desorption or collapsing of stabilizing additives at particle surfaces facilitate the rapid onset of aggregation. This is commonly achieved through changes in pH or temperature or through the addition of a co-solvent to increase additive solubility in the continuous phase. Many products use switchable polymeric stabilizers, for which exposure to the atmosphere, changes in temperature, or other triggers change surface conformation and result in rapid destabilization. We have described colloidal stability in terms of an interaction energy diagram. This is an effective approach because it builds on our existing understanding of chemical kinetics and activation energy. So let's continue with this model for examining other influences on the rate of aggregation. Our focus thus far has been on van der Waals attraction and electrostatic repulsion, which compose DLVO theory. An emphasis was placed here because these interactions are most common in hydrophobic colloids. For example, in commercial systems, the additives used to generate a hydrophobic colloid are typically anionic surfactants and polymers. However, due to limitations on achievable charge densities, often additional interactions are necessary to shore up stability. This is often accomplished using steric interactions. Additives used for this are those that produce a layer of molecular chains that interact favorably with the surrounding water. Examples include high molecular weight amphiphilic polymers that absorb with large loops and tails, providing for molecular chains that extend well into the aqueous phase, and long-chain non-ionic surfactants. Conceptually, the presence of molecular chains at the surface enhances stability in a couple of ways. First, it expands the size of the particle with a low-density layer that reduces the composite Homaker constant. Much more important is the overlap of such chains, which reduces hydration, increasing the enthalpy, and limits chain flexibility, decreasing entropy. In other words, free energy is increased, and thus work is required to intermix such layers. Furthermore, this process will encounter significant osmotic resistance. We often think about steric repulsion as an independent contributor to the overall repulsion, but it is important to remember that often even the additives themselves are designed to conflate these influences. For example, protective colloids are typically anionic polymers with sufficient amphiphilic character that they provide both electrostatic and steric repulsion. This is so common that the phrase electrosteric stabilization is frequently used to describe how many additives work. As discussed in the chapter on molecular interactions, charge-dipole physical bonds are strong enough to orient surrounding water molecules to optimize the interaction. This structuring effect decreases with distance but can extend out several water layers. This occurs to a far lesser extent, if at all, when only van der Waals interactions such as hydrogen bonding are involved. For particles that possess charged functional groups or retain adsorbed charged species within their stern layer, the close approach of their surfaces in water produces an increase in free energy. This results from the enthalpy change involved in the displacement of hydration layers, and is the origin of a repulsive energy which inhibits particle contact. The strength of such interactions is small relative to electrostatic interactions, but they're appreciable enough to make a significant contribution to colloidal stability. Hydrophobic attraction is sometimes explained using the decrease in particle surface area. Although this is an energetically favorable process, the reduction in surface area in the case of solid particles is quite small. Thus, it would appear that this is more than simply a favorable surface process. As we have discussed, water expands when it freezes, forming a low-density solid structure. This expansion is necessary to optimize hydrogen bonding. Water undergoes similar structuring on a smaller scale when it encounters hydrophobic molecules or molecular components, for example, surfactant hydrophobes, in what sometimes is referred to as hydrophobic hydration. For particles lacking in charged or polar functional groups with the ability to physically bond with water, it is likely that water molecules in the surface region undergo similar structuring. As particles closely approach each other and colloidal forces become a factor, it is likely the volume available to the remaining water is reduced, forcing an increasing abandonment of the optimized hydrophobic hydration-like structure. The high-energy water relative to that in the bulk promotes the aggregation of particles. Although this effect is poorly understood, and some have argued it is complicated by the formation of small air bubbles, it is believed to possibly play a major role in determining colloidal stability in aqueous systems. Here we pause for a moment to pull together what we've covered so far and to put it into context. As discussed, particle collisions are a result of Brownian motion and/or hydrodynamic forces, for example due to mixing. It's only when the particles are separated by a distance on the nanometer scale that colloidal forces begin to dominate the interactions. Such interactions determine whether or not collisions result in the particles binding together irreversibly. DLVO theory was the first quantitative description of the role played by colloidal interactions in determining the stability of a colloid. It considers exclusively van der Waals attraction and electrostatic repulsion. Although the Hamaker constant for the interaction between particles can be negative, this is rare, and van der Waals attractive forces tend to dominate in most systems, as do electrostatic repulsive interactions. In some cases, usually when cationic polymers are used to destabilize a colloid, as in the case of patching, electrostatic interactions can be attractive. There are also other attractive interactions that can contribute, such as hydrophobic attraction. And polymers can be used to essentially tether particles together in a process known as bridging. In commercial products and in nature, steric and electrostatic stabilization are often used in combination. This is through additives that provide for both, or use of separate additives such as the combination of an anionic and non-ionic surfactant. In addition to electrostatic and steric, there are other repulsive interactions that can help stabilize a system. However, these are usually not controllable, but their influence can be significant. The most important of these are hydration forces found in aqueous colloids. So, when examining a colloid, keep in mind that there may be a number of interactions in play, but usually only a few dominate. Controlling these provides for control over the stability of the colloid. Finally, it should be emphasized that for hydrophobic colloids, stability refers to kinetic stability. Such systems are always undergoing destabilization, and stability is a measure of the rate of destabilization relative to a given time frame. The maximum in the interaction energy provides the energy barrier to primary aggregation. This is an irreversible process. Although the secondary aggregation is possible at greater separation distances, these interactions tend to be quite weak, providing flux that are readily redispersed. Thus, the conceptual model provided here is quite useful in explaining changes in stability based on modifications to particle interactions. For example, adding a non-ionic surfactant to electrostatically stabilized hydrophobic colloid will likely increase the repulsive energy and thus increase the energy barrier to aggregation, slowing it down and providing increased stability to the hydrophobic colloid. For colloidal systems in which electrostatic repulsion plays a major role, zeta potential is a good gauge of stability. In fact, it is really the only experimental information available on the nature of the electric double layer. Here's a schematic for a surface that develops negative charge in water and the Stern layer that accompanies it. Electrokinetic phenomenon involves inducing steady-state tangential flow of the liquid phase relative to the charged solid surface under isothermal conditions. The electric potential at the slit plane is defined as the zeta potential, which can be estimated from electrical measurements made during electrokinetic processes. As discussed earlier, the connection between zeta potential and colloidal stability is based on the assumption that it is approximately equal to the electric potential at or just outside the Stern plane. There are situations where this assumption becomes tenuous, for example when steric stabilization makes a major contribution. Thus, interpreting results of electrokinetic measurements requires a good understanding of system composition. Here, we focus on arguably the two most popular techniques for the measurement of zeta potential: electrophoresis for particles and streaming potential for pads or plugs formed from colloidal particles. In electrophoresis, particle motion is induced relative to the surrounding liquid. This is done by applying a potential across the cell holding the colloid. The zeta potential is calculated from the average particle electrophoretic mobility, which is the electric field normalized particle velocity. In streaming potential measurements, a plug or pad of particles is formed. A pressure gradient is applied across the pad, usually by pulling a vacuum. This produces flow through the plug, creating a potential. The zeta potential is proportional to the ratio of the generated electric potential to the applied pressure gradient. In principle, electrophoresis measurements are quite straightforward. A colloid is placed in a cell and an electric field is applied. Velocities are measured as particles move towards the oppositely charged electrode. The temperature dependency of such measurements is implicit through the viscosity of the liquid. Early measurements of zeta potential were made in a manner not that different from what is represented here. Velocities were measured using a stopwatch by monitoring particles with a microscope through an etched eyepiece. Besides being quite time-consuming, the most challenging aspect of this type of measurement is finding the stationary layer, where a process known as electroosmotic flow does not influence particle movement. Nowadays, electrophoretic mobility is more commonly measured using laser Doppler velocimetry, or LDV, which is a more accurate and more convenient approach. Measurements on more concentrated colloids can be made using electroacoustic techniques. Because particle velocity is proportional to the strength of the electric field, applied velocities can be normalized with the magnitude of the field. Such values are known as electrophoretic mobilities, which is an intensive physical property of the colloid, having SI units of meters squared per volt seconds. However, mobilities are more often reported in terms of micron centimeters per volt seconds, with typical values ranging from negative to positive 5, with the sign indicating whether the particle is carrying a net negative or net positive charge, respectively. Derivations relating electrophoretic mobilities to zeta potential have been posted on the Moodle site. The Huckel equation is used in cases where the Debye-Huckel parameter multiplied by the particle radius is small. In other words, for extremely small particles and or a thick electric double layer. The Smolakowski equation applies at the other extreme, where the Debye-Huckel parameter multiplied by the particle radius is large, that is, for larger particles and or a thin electric double layer. This scenario is much more common. For example, the Smolakowski equation applies for the particle size of 1 micron and an ionic strength of 1 millimolar or greater, and furthermore, it applies to non-spherical particles. Between these extreme scenarios, zeta potential can be estimated from the Henry equation for low potentials less than about 25 millivolts in magnitude. There are also theoretical estimates for conditions for higher potentials. Some authors simply report the electrophoretic mobility when the system conditions are within this intermediate region. Streaming potential measurements can be used for particles not well suited for electrophoresis. Here, a pad is formed from the particles. The pores passing through the pad can be treated as a collection of capillary tubes. The surface of one of these capillary tubes possesses the same charge density as the particles that form the mat structure. As a result, an electric double layer forms when these openings are filled with water. Thus, outside the stern layer, the pore volume is entirely composed of the diffuse layer, which for negatively charged particles is enriched with cationic counterions. For this measurement, a pressure gradient is applied across the pad of particles, which induces flow through the capillary pore structure. Beyond the slip plane, the counterions are carried by the convective flow. However, movement of the counterions away from the surface charge that they neutralize produces a potential and thus an electric field, which counters the hydrodynamic forces. When forces on the ions are balanced, the steady-state potential value is known as the streaming potential, which is directly proportional to the applied pressure gradient. The proportionality constant is related to the zeta potential of the pore surfaces and thus the particles. Measurements typically involve the varying of the pressure gradient to produce a range of streaming potential values. The slopes of the linear fits of the potential versus the pressure gradient provides zeta potential values. This technique is well suited for particles that are difficult to keep suspended in a liquid, such as fibers. This example asks us to estimate the zeta potential for fibers given the table of data. Streaming potential measurements are common in industries that process fiber in aqueous streams. The measurement is made by pulling a vacuum to form a mat on a screen or support. Here's the equation we discussed. As with most calculations involving the electric double layer, there are a few constants to contend with, and the units can be confusing. So let's obtain values for the constants in SI units and rewrite the equation for the specified conditions. Next, we plot and fit the data. Here is the equation from the linear fit. From the slope, we obtain the zeta potential. A major advantage of this approach is that the particles do not have to be suspended to obtain a measure of zeta potential. For a slurry of fibers, electrophoresis often requires that measurements be restricted to the smaller components, which are assumed to be representative of all the surfaces in the system. This is often a tenuous assumption. Another type of measurement carried out on colloids and suspensions is a colloid titration. Such measurements usually involve the addition of a cationic polyelectrolyte titrant to a system containing a number of anionic analytes. These include suspended solids such as charged particles and dissolved solids including anionic polyelectrolytes and surfactants. Small organic ions and electrolytes do not participate in this titration. Rather than quantifying specific components involved, titrations gauge the capacity of a colloid or suspension to consume cationic charge, which is why the titration is often referred to as cationic demand measurements. This is a practical measurement, which provides an estimate of the amount of charge required to consume dissolved anions, the so-called anionic trash, in addition to the anionic solids. The titrant solution typically contains 1 milliequivalent per liter of a high charge density, low molecular weight cationic polyelectrolyte, such as 3,6-ionine, also known as polybrine, polyepichlorohydrin dimethylamine, or EpiDMA, and polydiallyl dimethyl ammonium chloride, or polydadmac. Polydadmac is the most frequently used. Also listed here is the anionic polyelectrolyte commonly used in back titrations, polyvinyl sulfate potassium salt, or PVSK. Three main categories of reactions account for most of the cationic demand. These include polyelectrolyte complexation to form scrambled polysol complexes, which form with nearly a 1-to-1 charge stoichiometry, surfactant polyelectrolyte complexes, which are assumed to form with a 1-to-1 charge stoichiometry, and adsorption of the cationic polyelectrolyte to anionic particle surfaces. This final reaction is difficult to characterize if dealing with porous solids. The polyelectrolyte should adsorb with a flat conformation, but the solids may possess charge that is not accessible to the polymer. Thus, the polymer used should be representative of the polymers that are actually applied to destabilize the colloid. There are two types of titrations used to measure the capacity a colloid or suspension has for cationic charge, that is, to measure its cationic demand. We begin with the back titration method, which requires only the apparatus necessary to carry out quantitative wet chemistry techniques, such as a balance and calibrated glassware, including pipettes, volumetric flasks, burettes, and so on. For this technique, we introduce a known volume of a cationic polyelectrolyte, the titrant, to a colloid of a known volume and solids level. Usually, a dilution of the colloid is made with water, making color changes more detectable. The cationic polymer is added in excess to consume dissolved anionic polymer and surfactant species in complexation reactions, and if present, saturates surfaces of negatively charged suspended solids. An indicator dye, usually toluene chloride, also known as O-toluidine blue or OTB, is then added to the colloid, which turns it a faint blue color. We then titrate with an anionic polyelectrolyte of known concentration. The polymer used for this is usually PVSK at a concentration of 1 milliequivalent per liter. PVSK has a high affinity for the excess cationic polyelectrolyte, which is consumed first, forming polysol complexes. Once gone, PVSK begins to complex with the cationic O-toluidine blue. These complexes give the solution a faint pink color, which indicates the titration endpoint. Often achieving a detectable color change requires a relatively high concentration of such complexes. A blank can be run with OTB and water to provide more accurate endpoints. Also, characterization of cationic demand by solid components requires determination of the oven-dried mass of suspended solids. Here, calculation of cationic demand using the added volume of the blank, titrant, and back titrant is shown. The total cationic demand in a colloid is broken down into two contributions: the soluble cationic demand from the dissolved polymers and surfactant species, and the particle cationic demand. Finding these requires a titration of the entire colloid or suspension and its titration subsequent to filtration. Filtration is usually carried out using a 0.45 micron pore size filter membrane, but a 0.2 micron membrane is sometimes used as well. Finally, the calculation of the solids cationic demand is shown using the particle cationic demand and the solids level of the colloid or suspension. The second type of titration used to measure cationic demand is a direct titration using a so-called charge analyzer. The charge analyzer consists of a Teflon cup and piston. As the piston moves up and down at a constant frequency, the colloid or suspension sample flows down and up, respectively, through the capillary opening. The voltage difference over the flow region is monitored as a cationic polyelectrolyte solution is added. The titrant is added to an endpoint of 0 voltage. The voltage is the streaming potential. As the colloid is added to the cup, some of the anionic material adsorbs to the cup surface, providing it with a negative charge and a negative zeta potential, which is directly related to the streaming potential. As the negative charge is neutralized by the titrant, the zeta potential and thus the streaming potential decline, eventually reaching a value of 0, the endpoint of the titration. Here, calculation of cationic demand for the direct titration method is shown. Determination of the various measures of cationic demand reviewed for the back titration method apply here as well. This completes our chapter on hydrophobic colloids, sols, and colloidal stability. As with the others, our discussion barely scratches the surface. Many colloid courses focus almost exclusively on colloidal stability. The critical point from our discussion is that hydrophobic colloids are thermodynamically unstable systems, and we use the term stability to describe kinetic stability. Our discussion used dispersions of solid particles to introduce concepts of stability. We began with the practical topic of particle sizing, which led to a brief demonstration of how particles in the colloidal size range possess a certain degree of stability just due to their slow sedimentation or creaming. We then discussed the origin of aggregation processes and introduced the Homaker constant, noting that for particles, London interactions are more robust and longer range. In Lecture 2, we also began our discussion on the electric double layer with the Gouy-Chapman model. This description was modified to include the Stern layer, which helped define the Zeta potential. With the van der Waals attraction and electrostatic repulsion defined at the particle scale, we summarized DLVO theory and briefly introduced other attractive and repulsive interactions. In the next chapter, we will examine two other hydrophobic colloids of significant commercial interest: emulsions and foams.